So welcome back. We're going to continue talking about continuity there. So there's not too many keywords today, which means some of them are easy and some of them are a bit tougher to think through, but we'll make our way through it. So we'll begin by discussing a few more properties of continuity. So our first theorem, 2.11, is going to tell us how we can take functions we know are continuous and build more continuous functions. So it says that if b is a real number and f and g are continuous at x equals c, then the following functions will also continue to be continuous at c. So the first property says if you've got a continuous function f, you can multiply it by any number you want, and it's still going to be continuous. So this means x squared, that's a nice continuous polynomial function, so by property 1, 3x squared is also going to still be continuous. Property 2 here says that you can add and subtract continuous functions. So now that we know that these two functions are continuous, we can take 3x squared, we can add to it an x squared, and we're still going to be continuous. Next, products of continuous functions are continuous. So now we can take our 3x squared, multiply it by x squared, get 3x to the fourth, still continuous everywhere. And finally, we can take quotients, as long as we don't divide by 0, right? The biggest thing that messes up a function is dividing by 0. Also taking square roots can be trouble. So 3x to the fourth divided by x is actually not going to be continuous at x equals c. That's a really bad continuous, but it's not going to be continuous at 0 because we don't want to divide by 0. Well, we need to be always vigilant of this. We can't just go ahead and cancel this. It really is a function where you can't divide by 0. Now we really do already have a huge class of continuous functions. We know that all polynomials are continuous. You can draw their graphs nicely. Rational functions are continuous, except of course at the points where we have holes in them. Same with radicals, trig functions, logarithms, exponentials. We have very many functions that are continuous at very many places to play with. Most functions you encounter that are of practical use will be continuous at most places. One really fun function actually that isn't continuous is called the Dirichlet function. So it's named after a mathematician who really thought of a lot of crazy functions, and what he said was, let's think about a function, takes x as an input, any real number, and its output's going to be 1 if you give it a rational number, and 0 if you give it an irrational number. So just to review, remember that rational numbers take the form p over q, where p and q are integers. So these are our nice fractions. 7/5, 2 over 1, 1/2, 3/4. Anything you can write like that, or you can write it as a decimal that stops, that's a rational number. And all the other real numbers that are not are irrational. So let's think what this function looks like. Well, if you put in 0, it's going to be 1. If you put in 1, 2, 3, 4, if you put in 1/2, 1 and 1/2, 2 and 1/2, any nice number is going to be given the value of 1 in this function. The problem is there's lots of irrational numbers. For instance, down here we have the square root of 2 is irrational. We have pi is irrational. And in fact, in between any two rational numbers is an irrational, and same thing goes there. So if you try to graph this function, most computers actually won't, well, computers will let you graph it, but your calculator certainly won't. What you'll get is a bunch of dots up and below. And this function is actually never continuous anywhere. The problem is it's just bouncing up and down too fast. There's a dot up here, then a dot there, then a dot up there, up there, there, and it's just a whole mess, but it's a pretty fun function. So remember that another thing we can do with functions besides adding, subtracting, multiplying, dividing is we can also compose them. And once you start composing functions, you can really mess with their continuity. It might not look anything like what you would expect. So let's start by looking at our example of f of x equals 1 over x minus 6. And hopefully you can recognize that this function is going to be continuous except when x equals 6. That if we try to put 6 into this function, we're going to try to divide by 0, and that's going to be a problem. We can also think about the function g of x equals x squared plus 5, which is going to be nice and continuous everywhere. It's just a good polynomial. But now we want to think, well, what happens if we tried to compose these functions? What would happen? So let's build a new function h of x, which is f composed with g. So this is the function where we're going to take the g function and put it into the f function, and so what we end up with is 1 over x squared plus 5 minus 6, and if we simplify it down a little bit, this is x squared minus 1. So now we see that we have problems that x had better not be 1 and negative 1. So it's going to be discontinuous at these points, 1 and negative 1, because it'll make us try to divide by 0. And the reason this happened is because these two values, 1 and negative 1, make the function g of x equal to 6. So that makes us put 6 into the function f, which is the place where it's discontinuous. That is, 1 and negative 1 make the inside function 6, which gives f an input of 6, which make it discontinuous. We can also think about the composition in the other order, g of f of x. In this case, this means we need to put the function 1 over x minus 6 into the function g, and so this becomes 1 over x minus 6 quantity squared plus 5, which again will be discontinuous at x equals 6. The outer function g is good. You can put any number into it you want, so we don't need to worry about what f does, but we do need to worry about putting the number 6 into the function f, because that could make it discontinuous. So now we've come to a theorem that's so important they didn't just give it a number, they gave it a name, which means you should know this theorem because you're going to need to know it quite a bit. So this theorem has 3 things that need to be true so we can deduce a certain conclusion. So it says first, let's start with f, some function, and suppose that f of a is not equal to f of b. So we'll just draw a schematic here to show what this means. So we've got down here a point on the graph of our function. We'll label it f of a. We've also got a point on here on our function f of b. And what property 1 simply is telling us is that these cannot occur at the same level. So we've got that checked off. Second, f needs to be continuous on the closed interval a to b. So we need to be able to go from a to b in a nice continuous manner. So we can sketch that in. It can look something like that. I don't really know what it is, but that's pretty continuous, right? Every dot is filled in. There's no open circles. There's no breaks in my graph. I was able to draw it in one smooth motion. So part 2 is checked off. 3. K is any number between f of a and f of b. So what this means is I'm going to go on my output axis, my vertical axis here, and I'm going to pick anything I want. Let's pick a nice k, say, here. So that's done. The conclusion says then that there is at least one number c in the interval ab so that f of c equals k. So what this is telling me is that somewhere in here between a and b there's a c so that f of c equals k. So basically what it is if I take k and I go over to my graph here, I need to be able to hit something so that I can go down and grab a c, so that in this case f of c equals k. So this means for a continuous function here, what I've got is I've got to hit every single value in between. I have to actually go ahead and hit all of my output values at least once. And the key is at least once. We can see that there's another place over here, let's call it c1, so that f of c sub 1 equals k, and in fact there's even another point here, c2, f of c2 equals k. There are many places, but I have to hit every single output from my function at least one time. Let's see how this can be used in a couple problems. So here's an example where you could use the intermediate value theorem. So the question is, will the function f of x equal x squared ever equal the value pi on the interval 1 to 3? So it might be really hard to guess and check to see if this works, but the intermediate value theorem provides us with a way to figure out if it will or not, but not necessarily where it will happen. So we need to check 3 things. First, what we need to say is we need to check, well, let's see, f of 1 equals 1 squared, f of 3 is equal to 3 squared, and 1 is not equal to 9. So this is the first property of the intermediate value theorem. We can't be equal on the endpoints. 2, f is certainly continuous, as f is a polynomial. Therefore, it'll be continuous on the interval 1 to 3. And last, we need to check, well, it is true that 1 is less than pi is less than 9. And remember, these are the values on our endpoints. So what this means is that by the intermediate value theorem, there is going to be a c with 1 less than c less than 3 that is on our interval, so that if we put this value c into our function, we're going to get out pi. Now I don't know what number this is, doesn't really help me there, but it at least tells me that somewhere in between 1 and 3 I can put a number into my function and I get out pi. Now this is also a good example that you should follow whenever you're solving problems using the intermediate value theorem. You really need to show the 3 steps and then your nice conclusion: by the intermediate value theorem there is a c that makes the statement true. So now we've got one of the best applications of the intermediate value theorem, the following question. And you should think about it to yourself before you look at the answer. True or false, you were once exactly 3 feet tall. So please pause the video and really think through this, whether or not you believe this. Is there ever a point in time when you were exactly, and I mean exactly, 3 feet tall? So hopefully you've thought about it and you feel one way or the other that there was a time when you were 3 feet tall, but hopefully I'm going to be able to actually convince you that this thing is true, that it's true there was a time when you were 3 feet tall. So we're going to let height of t be the function that measures your height in feet where t is time. Okay, so you're going to put in some time into this function and it's going to tell you exactly how tall you are. So we've got 3 things to check. First, certainly the height when you were born is not the height you are now. Most people grow throughout time. Hopefully you are actually in fact taller now than you were when you were born. I bet by some good amount. Next, your growth is continuous, so the function height of t is continuous on the interval born to now. There are no big jumps in your growth. Even if you think you had a growth spurt that still took time, it still happened over a little bit. You didn't blink your eyes or in half a second grow 12 inches or anything like that. Your height is continuous. And finally, 3 feet is between the height when you were born and the height now. You weren't born 3 feet tall. You were probably born something under 2 feet. And right now, I'm willing to bet everyone is over 3 feet tall. Therefore, by the intermediate value theorem, there is a time c on the interval between born and now where your height was exactly 3 feet. I have no idea what time this was. We probably can't even actually figure out when it was, but we at least know there was a time when this occurred. So you have 2 more problems on a sheet you got yesterday, or is available online for you to try to figure out, that are related to this idea of trying to figure out exactly when something happened. Also, there's some problems posted on the website for you to try. These are in your book. And also, please post a question to Blackboard. If you have any questions, please let me know. Thanks.